Hello everyone, I hope you are doing well. In this video, we are going to talk about atomic form factor or atomic scattering factor. So both of them are equivalent terms. Atomic form factor is also known as atomic scattering factor, which is represented by a symbol small f. Okay, in subscript we usually name the element whose atomic scattering factor is being mentioned, but normally small f is a symbol. This is a parameter or a concept that has been introduced in scattering theory when we are considering scattering involving atoms in them. Okay, because you can see from the name that it is atomic scattering factor, which shows that it is the factor that tells us that how well an atom can scatter something that is interacting with them. For example, it could be an X-ray beam, it could be a neutron beam, or something like that. And this factor tells us that how well an atom can scatter that incident beam. And it's really important to know because it helps us to do some mathematical calculations and we need to calculate it. All right, so let's quickly get started with the introduction. As we are linking this concept to X-ray diffraction process, we are here from the crystal theory, so we wanna learn this concept for finding out the scattering amplitude or geometrical structure factor, or simply structure factor, that whatever name you prefer. Let's start writing, and whatever I'm gonna write is something that you can write on paper as a response to this question if someone asks you to define it and elaborate that concept, or you can tailor the explanation according to your needs. Okay, so let's start with the introduction and then we'll write the definition and mathematical formulas of atomic scattering factor, and meanwhile I'll also explain each and everything. Okay, so when X-rays or incident on the lattice planes they interact with the atoms of the lattice, because because it is the question, it is the central question to ask that why X-rays are scattered. They are scattered because they are interacting with something. And what is that something? What is the lattice made up of? It is made up of atoms. So X-rays are actually interacting with the atoms of the lattice, and those atoms are actually scattering the X-rays. Now let's see what happens further. After interacting with the atoms of the lattice, X-rays gets deviated from their original path, from their original path as a result of that interaction with atoms. Now, atom is made up of nucleus surrounded by the electronic cloud. Now, let's see what actually significantly diffracts and scatters the X-rays. Since the atomic nucleus is really tiny, it's tiny, heavy, and concentrated, which means it has a lot comparatively greater density as compared to the electronic cloud, and it's not that much vast and spreaded as compared to the electronic cloud. That is why X-rays do not actually and mainly interact with the atomic nucleus, but they interact with the electronic cloud. So the nucleus doesn't contribute as much to this process, and we can ignore the influence of the atomic nucleus to the X-rays, and hence we can only consider the influence of the electronic clouds on the X-rays. Okay, that is how we can say that since the atomic nucleus is really tiny, it's really small in size, it is heavy, concentrated, and it's heavy concentration. Since the atomic nucleus is tiny, heavy, concentrated, dense, and screened by the electronic cloud, we know about the concept of shielding effect. The electronic cloud acts as a shield and it protects the atomic nucleus from the other waves. Okay, so the waves cannot directly reach to the atomic nucleus. They have to pass through the electronic cloud first, and if they are powerful enough to penetrate through the electronic cloud completely, then they can reach the atomic nucleus and interact with them. And for that purpose, very energetic, highly energetic rays are needed. For example, gamma rays can interact with the atomic nucleus, but X-rays mainly couldn't do that. Okay, so X-rays do not mainly interact with the atomic nucleus, but they interact with the electronic cloud. All right, so these are the reasons that we can give to justify our stance on the fact that the atomic nucleus is negligibly influencing and scattering the X-rays. All right, and we can consider the electronic cloud later on in our discussion. So whenever we are talking about the interaction of X-rays with atom, we are actually talking about the interaction of X-rays with the electronic cloud, because it's electronic cloud actually basically that is scattering the X-rays in an atom. So the electronic clouds are the only component, major component you can say, of the atom that scatters X-rays significantly. The X-rays scattered from one part of the cloud, or you can say atom, interferes with the X-rays scattered from the other parts of the cloud or atom. We are talking about a single atom here. Okay, I'll elaborate that right now. At all angles to produce a resultant diffracted waves in certain directions only. Now what we are saying here is that first we said that what happens when X-rays are incident on the lattice planes, they interact with the atoms of the lattice. Okay, now let's consider a single atom. What happens with a single atom? And if we know what happens with a single atom, then we can tell about the other atoms as well, and then we can link it to the unit cell. So if we talk about the atom is made up of atomic nucleus. It has a nucleus, which is atomic nucleus we are saying here, and an electronic cloud around the atomic nucleus. Okay, what about the atomic nucleus? Do X-rays interact with the atomic nucleus or not? No, they do not considerably interact with the atomic nucleus. The interaction is really negligible, so we can neglect it, and it's okay to do that. The atomic nucleus is tiny, heavy, concentrated, dense, like it is really small, and it is screened by that electronic cloud. That is why The electronic clouds are the only components of the atoms that scatters the X-rays significantly. That is something that we can easily understand. Now next what I wrote is that X-rays scattered from one part of the cloud interferes with the X-rays scattered from the other parts of the cloud at all angles to produce the resultant waves in certain directions only. Now let us see it on the paper. All right, let's say we have that an atom. Okay, this is the atomic nucleus and this is the cloud, electronic cloud around it, and we have many electrons in it. All right, we have many electrons in it. When a X-ray beam, when X-rays are bombarded on an atom, this is a single atom, we are talking about a single atom here. When a X-ray beam comes here, electrons are the charged particles. Okay, if you know how to generate electromagnetic waves by Maxwell's equation tells us that how electromagnetic waves are generated. It is generated when the charged bodies are accelerated. Okay, so when an electromagnetic waves hits a charged body, like electron is a charged body, electrons begins to oscillate with the same frequency as the electromagnetic wave has. Okay, X-rays has some frequency, some wavelength, okay, some speed, so they have some frequency. They begin to oscillate with the same frequency as the X-rays has, and this oscillation produces X-rays, regenerates the X-rays in all directions by one electron. This is something that is happening by one electron, for example. Then we have many electrons inside the atom, so that we can call as, since it's a charge distribution and we know that we cannot localize the electron to a certain position, they're always moving, so we can say that uh, X-rays from one part of the atom, okay, these X-rays, let me um, draw that each electron is producing X-rays in all directions. They are producing X-rays in all directions. There is no preferred direction. They are producing in all directions, each of them. Okay, so now these X-rays generated by each of the electron will interfere with each other, since they are waves. When waves come across each other, they interfere with each other. Okay, either constructively or destructively. Where they are interfering constructively, they will produce a resultant diffracted waves in certain direction. When they interfere destructively, the waves are gone. Okay, we can't see them, we can't detect them, but the ones that showed constructive interference will be diffracted in certain directions only, not in all directions. Not all directions are possible, because we know that the destructive interference is also happening inside the atom. Hence, in certain directions only the diffracted waves will be found, not in all directions, but in certain directions. What is the reason? Because we have a charge distribution instead of a single electron. If it would have been a single electron only, then it would have produced the X-rays and diffracted them in all directions. Okay, that is something we can see here. But here what we have is destructive interference as well. We have so many electrons in it, and it's a charge distribution, a spherical charge distribution, and we cannot allocate them a definite position, and we have this cloud. So one part of the cloud interferes with other parts and produces a the X-ray scattered from one part of the cloud interferes with the X-ray scattered from the other parts of the cloud at all angles, at all possible directions, because it's in 3D. Okay, we are seeing a 2D version here, but it's a 3D. So in all possible angles, they interfere with each other and produce resultant diffracted waves in certain directions only. That is what I'm saying here. And here we are talking about a single atom. Okay, now we have inside a unit cell. Inside a unit cell there are many atoms. Okay, this is, let's say, a atom. This is one atom. We have another atom here. We have atom in here in simple cubic, for example. We have atom at each of the corner. So since we have many other atoms inside the unit cell, so what happens is, now they all will produce net waves in certain directions only, and their waves interfere with each other either constructively or destructively, and their interference and their combination will result the geometrical structure factor of the unit cell. Okay, or that is also known as the scattering amplitude of the diffracted waves. Okay, their interference, their combination. Now here you cannot simply add their contributions up simply because their location are different. Okay, their relative positions matter as well, because one is located here, one is located here. Their relative position, because we know that the part difference matters a lot in interference process, so their locations matter where these atoms are located. Okay, so the factor of location is introduced as well, what an atom as alone is behaving, which is determined by the atomic form factor, and what is the location of other atoms relative to each other. That is something that is dictated and accounted by their position vectors, you can say, and we'll see it in geometrical factor part. All right, but here we are only considering the atomic factor part, which is related to a single atom. All right, so yes, that is the main phenomena. I hope you got it. Now let's write it and continue what we were writing. Now let's write what will happen next, and after writing it down, we'll merge it to the definition of atomic scattering factor, because doing so, doing these explanation, we will feel the importance of introducing atomic scattering factor. Okay, we can justify why it was needed to define. Now we have many atoms inside unit cell, so the resultant diffracted beam is obtained by the interference of waves from all the atoms located at different positions in a unit cell. You can draw the diagram as well, the diagram that I have drawn here for the simple cubic unit cell. You can mention the figure A. This is figure A to show that we have atoms at different locations, to just to show this statement. That's this PO region. This is x-axis, this is y-axis, and this is z-axis. Okay, you can draw it. You can see this is origin, and this is r1 vector, for example, r2 vector. You can do this. Okay, just to add definition, this process involves two distinct contributions. This whole process, we are talking about the whole process in general. After these lines, after concluding the introductory part, we'll write the definition of atomic scattering factor. Okay, first is scattering. We have two distinct phenomena here. First is the scattering from electronic cloud or electrons, in simple words, in the same atom, in the single atom, which is accounted by the atomic scattering factor represented by symbol F. Okay, so first thing to consider here, the two distinct things that are happening here, or to consider in mind while considering the interaction of X-rays in a unit cell with the atoms. The first process to consider is the scattering from the electronic cloud of a single atom, individual atom, that is mathematically given by the atomic scattering factor small f. And what is the second thing? Second thing is contributions from all the atom relative to their position. Okay, on the basis of their position, their second, the summation of this scattering from all the atoms in the unit cell. This summation gives us the scattering amplitude of the diffracted X-ray beam, which is also known as the geometrical structure factor. Okay, so I hope you got it. We should know the atomic scattering factor and the relative position of atoms inside the unit cell. Taking into account the contribution of all the atoms in a single unit cell, we can get the scattering amplitude of the X-ray beam that has been diffracted, or in other words, we can get the geometrical structure factor for the interaction. Alright, so we can write here in the brackets, first phenomena was the atomic scattering factor. So the second thing, the summation will give us the geometrical structure factor. Geometrical structure factor that we represent by symbol capital S. In some books it is represented by capital F, and it's totally up to you whatever symbol your book is using, so you can use it. So the second phenomena will give us the geometrical structure factor. Hence, the intensity of the diffracted beams primarily depends on the atomic scattering factor and the position of each atom in the unit cell. Doing so, we get a rule which tells us what to expect on the screen for a given crystal, for a given X-ray diffraction from a particular crystal. It tells us which planes would give constructive interference, which is maxima, in the process. Okay, as a result of X-ray diffraction, we get a pattern on the screen. Okay, for example, if it is a NaCl crystal, then its X-ray diffraction pattern will contain some intensity peaks. Okay, it will contain some intensity peak, and each of these peak is showing a maxima from a given plane. All right, do not mix these peaks with the order of diffraction. Order of diffraction is something different. Here we are only considering the first order diffraction, which has the maximum intensity for a given plane. Okay, so we are considering only n is equals to one plane. Here 2d sine theta equals n lambda. So for a given d, there could be many n. All right, so we are only considering n equals to 1, which is the brightest maximum that we get for a given plane n lambda. All right, so only one line we are considering here from one plane. Okay, from one plane we are considering only one line, which is the center line, which has the maximum intensity. So each line on the screen is showing a maximum from a particular plane. And how to know which plane would NaCl will have on the screen, like which planes will give maxima for NaCl crystal. So this is something that we want to know, and we can have this information if we calculate the geometrical structure factor from using these things that I have written here. We can calculate the geometrical structure factor by finding out the interference of all the waves from all the atoms in a unit cell. We'll get a formula. So that rule tells us that what to expect on the screen, like which maxima will we get and which planes will give this maxima. All right, so these are all the benefits. Hence, having this information, we can know a plenty of things related to crystals and their patterns on the screen. This is it. Okay, this is it for now. I write one more statement and then we'll write the definition of atomic scattering factor for which you are here. But these explanations are the cherry on the top, so they are crucial as well, so don't brag. Hence you can write brag intensities. Bragg intensities are actually the diffracted beams intensities, the one that we get. Hence the Bragg intensities of the diffracted X-rays from the various planes, as I told you people, from various planes, or the overall contributions of interaction of X-rays with all the atoms in the unit cell. All right, this is something that I told you people before writing this statement. Okay, I hope you got it. And this is the explanation that you can also write for introducing the geometrical structure factor, because this is introduction and it is common to geometrical structure factor and atomic scattering factor. In summary, what we saw so far was that when X-rays are incident on the lattice planes, they interact with the atoms, and atom is made up of atomic nucleus and electronic cloud. X-rays do not actually interact with the atomic nucleus. They couldn't manage to do that. They are significantly impacted by the electronic cloud, and electronic cloud is the one that is scattering them. Okay, so what we saw is that what part of atom is scattering the X-rays. After that analysis, we saw that since it's electronic cloud, and each part of the electronic cloud scatters the X-rays in all directions, so all their contribution interferes with each other at all possible angles, so that from a single atom we get diffracted rays in certain directions only. And to account for this stuff happening within a single atom, there are many things happening within a single atom which results diffracted beams in certain directions only. To account for this thing, we introduce atomic scattering factor. Okay, atomic scattering factor is central thing that defines what's happening inside an atom. All right, then we saw that since we are considering a unit cell and there are more than one atom inside a unit cell and their locations are different, so their relative location matters, and their net contribution will give us the geometrical structure factor, which will give us that what diffracted beams we will get from this whole unit cell. What we'll get from one atom is dictated by the atomic scattering factor phenomena, and what we'll get from this unit cell is dictated and represented by the geometrical structure factor. Okay, that is something that we saw so far. Let's define atomic scattering factor or atomic form factor. It is actually the quality of an atom or capacity of an atom to scatter the X-ray beam. Okay, it is a measure of how well an atom can scatter the X-ray beam. So it is just a factor that tells us the quality or the capacity or the strength of an atom to scatter the X-ray beam. Greater the atomic scattering factor, greater the ability of an atom to scatter the X-ray beam. This is the reason the atoms with the higher atomic number have a higher atomic scattering factor. This is because their electronic cloud is huge and they are capable of scattering the X-ray beam considerably as compared to those atoms that have comparatively less atomic number. For example, if you consider a NaCl crystal, it is a good example of a crystal that has two kinds of atoms in it. The X-ray beam that hits the sodium atom is scattered less as compared to the one that is interacting with the chlorine atom, because chlorine atom has a higher atomic number. It has maybe 17 atomic number or 19, I don't just remember it exactly, but sodium has 11, and hence it will scatter the X-ray beam less as compared to the chlorine atom. Chlorine atom will scatter it more. So chlorine atom will have a higher atomic scattering factor while sodium has a lesser atomic scattering factor. It is not a direct measure, like atomic number is not a direct measure, but it's a consequence of the formula and the definition that we had defined. In general, it satisfies that the atoms with the higher atomic numbers have a higher atomic scattering factor or atomic form factor because they have more team, a greater team to scatter the X-ray beam. Alright, now let's see how we can define atomic scattering factor. Let me write the definition and all that stuff first, and then I'll make you understand what each statement means and how we can justify it. So let's start writing. The atomic scattering factor is the measure of the efficiency of an atom in scattering the X-rays. Mathematically, it is the ratio of scattering amplitude of X-rays scattered from a single atom or its electronic cloud, you can say, to the scattering amplitude of X-rays scattered from a single electron, from an electron, you can say single electron, up to you if you want to specify, but it's a single electron. From my electron means it's a single electron located at a point which is localized at a particular point. Okay, we'll understand it. We can write it in the form of mathematical uh, rule as well. F, which is the which is the atomic scattering factor, it is equals to brackets scattering, the same thing that I have written here, amplitude of X-rays from a single atom or electron cloud. It's from a single atom in general, but in case of X-ray diffraction, we know that it's electronic cloud. That is why I'm writing here the electronic cloud. But in general, it's from a single atom, including the effect of nucleus. But we have neglected it. We can write electronic cloud as well, divided by the scattering amplitude from a single electron of X-rays from a single electron. This is the ratio. In mathematical form, if we find out, calculate this ratio, we will get the scattering factor, atomic scattering factor. Then we can proceed in terms of electronic density, which is Nj of R. N is the electronic density symbol. J shows which atom you are considering. As I told you people, a unit cell of NaCl has two kinds of atom. So electronic density of sodium, electronic density of chlorine would be different of R. So J represents which atom you are considering. Okay, R is the radial vector, since it's a electronic cloud which is having approximately a spherical distribution, spherical symmetry. That is why we are using R in spherical coordinates or in Cartesian coordinates, whatever the coordinate system is being considered. In terms of electronic density, it's Nj of R. We can find the atomic scattering factor for an atom by using following formula. One more formula, integral formula, can be used, which is actually derived from the basic definition, but we are not going to derive that formula here in this video. If you want me to derive it for you people, you can ask me in comment section, then I'll do that video for you people. So Fj, which shows that it is the scattering factor for the J atom, chlorine atom, sodium atom, whatever atom you're considering. So J shows which kind of atom you are considering. It is equals to Fj equals integral, and we will have the electronic density here multiplied by the position factor, which is minus iota g dot r dv. This is a volume integral, all right, that will be done over the whole space. This exponential function with a negative power on it and the position involvement, it shows that the atomic scattering factor decreases exponentially with increase in distances of electronic cloud of electrons from the nucleus or from the center. All right, it is understandable, because if you understand it from the fact that we have supposed a situation like this is the nucleus, okay, and there is the electronic cloud here, and r is the distance of the electron from the nucleus, okay, or we can also say r is the distance from of any given point where we want to find out the atomic scattering factor from the nucleus, okay, because the electronic density is not uniform throughout the cloud. It is concentrated somewhere and it is light somewhere, Okay, not all electrons are evenly distributed on the cloud. Over the cloud, we know the existence of subshells. There is S subshell, which has spherical symmetry. Then we have the P subshell, which has another shape, in which we can see that the electrons are concentrated right here. There is more probability of finding them right here than here. Then we have D subshell, which is another complex shape, and all these shapes and their areas shows the probability of finding the electron, and the probability is maximum here but minimum here. So electrons are not evenly distributed throughout the whole space. That is why we tend to find out the atomic scattering factor at each point in the cloud, and we integrate it our whole space to find out the total atomic scattering factor of the atom. We add all these chunks up that make up the cloud. Since atomic density uh, beyond the electronic cloud will be zero, because there is no electron in here, so there will be no scattering, as R is greater than the maximum um, point where the atom is, which shows the size of the atom. Let's say the size of atom is capital R. So at distance R greater than or capital R, the atomic scattering factor will become zero. So the volume integral is essentially what the atom size is. Okay. So as the R increases, the atomic scattering factor decreases. It means that if the X-rays are interacting with that part of the atom, it will be scattered less, while if it is interacting well inside the atom, like it penetrates deep into the atom, then it will be scattered more, because there is more density of electrons in here, more intense the factor would be. But we know that we take the contribution from the whole atom. That is, we add up all of the chunks, and all of the chunks add up to give us the whole factor, which is the atomic scattering factor small f. Okay, all of these factors, these small chunks, and all the effects of uneven distribution of electron is taken into account in this integral. Okay, this position integral ensures the fact that the influence and density of electrons inside an atom is not uniform, and this integral takes into account this fact that there is no even distribution. As I told you people, if you are inside a crowded place, there'll be more scattering, and if you are in a place where there is no much of the crowd, if it is less number of electrons present, then the probability of scattering is less, and hence the X-rays will be less scattered. And this factor takes into account this feature of interaction. Okay, this position factor in this integral, while this is the electronic density. As we can see, what is the electron density is different at different positions. That is why it is a function of R. All right, I hope you understood this main formula. Okay, now let's write something more about atomic scattering factor. What else we can say? You can even mention the things that I have told you people about this formula. Okay, how the electronic density is a function of R. You can write it as it is, like Nj of R. Electronic density is a function of position, and it decreases exponentially as we move away from the atomic nucleus. And this factor, e to the power minus iota g dot r, ensures the involvement of distance factor in relation to scattering phenomena. Okay, so that is something that we can write about it. Now let's continue what else we can write here. Nj of r is a function of distance r from nucleus of atom whose atomic scattering factor we want to calculate. Which atom? The atom whose scattering factor we want to calculate. All right, since electronic clouds
are not even. This and the scattering ability of atom decreases with increase in distance from nucleus until r is greater than capital R, where you can write in bracket that r is the radius of atom. R is greater than capital R, then the scattering ability of atom becomes zero, because since atom is finished at atom has a size, so it will be it will terminate at some point. It has some boundary. So when that boundary is surpassed, there will be no scattering. That is something that I'm writing here, and I'm saying that the scattering ability decreases with increase in distance from the nucleus, and it will be maximum nearer to the nucleus. Ability becomes zero. All these things, all these features are taken into account into above integral for atomic scattering factor of a whole atom, of an atom, you can say. Okay, so that we can assign a single value of scattering ability to an atom by adding up all of those small chunks of different behaviors. Since all the chunks are behaving differently, we can call each chunk as df, having a scattering factor of df, and we will add up all these chunks over the whole volume to get the net scattering factor for an atom, for the whole atom, by adding up all those chunks. Let's see the relation of atomic form factor or atomic scattering factor with the atomic number of the elements. So we can write that atomic form factor increases with increase in atomic number of an element. Since we'll have a greater members in a team to push or scatter the incident x-rays, that is why the atomic form factor increases with increase in atomic number. Because if we have a crowded place, then the probability of scattering is greater, you know that. Okay, and if we have several vacant spaces, then the probability of scattering decreases. This is a common daily life experience as well. We know that if you are in a mall and if it is really crowded, then we have to be scattered depending upon which spaces are available. This is how we behave, because we can't we are not electron like, and we are not x-rays, we are not electromagnetic waves, so we have to see the positions, the vacant spaces, in order to move. And the probability of scattering is greater in a crowded place, and that is why people tend to get joined together so that they may not lose each other. So yes, this is how we can write atomic form factor increases with increase. Hence the heavier elements or crystals or atoms have greater atomic form factor than lighter atoms. Lighter atoms, like in NaCl crystal or unit cell. Na chlorine. Cl has greater atomic form factor. since chlorine has a greater atomic number, I think 17, then sodium do. Okay, sodium has an atomic number of 11. It's a lighter atom, and chlorine is a heavier atom. That is why chlorine has a greater atomic form factor than sodium has. Next, if the atoms are assumed to be points only, are assumed to be points only, we can only assume that this is not a fact. So if they were points only, which means that all of the electrons are stacked over each other, and there is no concept of volume in here, then what happens that we know that the electronics, let me write that statement wholly, then we'll justify it to the extent I can with the information that I provided to you people. Then the atomic scattering factor is just equal to the atomic number or number of electrons present. That is atomic number of neutral atoms, not the ions. Neutral atoms, which is Z. We can easily justify this statement from the fact that we know that the atomic scattering factor is a ratio of the scattering amplitude by all electrons divided by the scattering amplitude by one electron. Okay, if all of the electrons are stacked over each other and they are at same distance, there is no concept of R, then there is no dependence on R, there is no volume element, and hence there will be no that patches kind of thing. So they all will scatter the x-rays the same way because they are same position, and there is no preference of one electron's position over other electron's position. Okay, in case of volume distribution, there was a preference of position. Some electrons could do it better and some electrons couldn't do it the way the other did, okay, because of the position. Hence all these electrons, which are, for example, if the atomic number is 3, so there are 3 electrons as compared to 1 electron could scatter it by, let's say, 1f time, then 3 electrons could do it 3f times because there are 3 of them and there is more power in here. And you can see, if you find out the ratio of 3f divided by f, you get 3, which is the atomic number of an element. Okay, this is understandable. If they were point objects only and all of the electrons are at same position, then their ability just increases by the number of electrons present. Okay, so scattering factor in case of a point like distribution will be equal to the number of electrons present, okay, or number of scattering agents present, which is capital Z in here. And they are saying the neutral atoms because, for example, if you are considering NaCl crystal, it is an ionic compound and it gives one of its electron to the chlorine atom, so it gets one of the extra electron, it loses one of the electron. It doesn't mean that you will consider 10 for sodium scattering factor calculation, not 11. That is not correct. Okay, you have to consider its neutral um, equivalent atomic number, which is 11. Okay, considering it as a neutral, what is its standard atomic number for its neutral state? So neutral states will be considered, not the ionic states. So even if it is NaCl crystal, you will consider 11 for Na and 70 for chlorine. Okay, let me write an additional piece of information that is also useful, and it will add volume to your answer if you want to extend it further. And I will not be able to justify this because it requires the derivation support. Like if we would derivate the expression for the scattering factor, then we we would be able to see that aspect of atomic scattering factor in its dependence on theta and lambda, or the scattering angle. So let's write it. The atomic scattering factor, let's see how the atomic scattering factor uh, is affected by the scattering angle. Factor of an atom falls off with increasing scattering angle, increasing scattering angle theta, or more precisely, if we say more precisely, with increasing value of sine theta by lambda. As shown in figure below, this relation can be depicted in a figure that I'm gonna draw right now. Here we are seeing the relation of atomic scattering factor with the scattering angle, and let's say it's 30, 20, 10, and we have f in this axis line, and here we have sine theta by lambda, and for aluminium it's somewhere between, the atomic form factor is somewhere, starts somewhere between here, above 15 but below 20. Okay, so it starts like that and it decreases exponentially. Okay, like that. This is for aluminium. This is experimental data. And then for zinc, we it starts from 30 and it remains like that, and then it decreases like that. This is zinc. Okay, you can draw it to show the relation of atomic scattering factor. This is figure, let's say this is figure 1, and it's showing the variation of atomic scattering factor with sine theta by lambda. Okay, so keeping a fixed theta scattering angle, if we change the lambda, which is changing the incident electromagnetic wave, changing the wavelength of incident x-rays, how the scattering factor will change. Okay, it shows that the scattering factor is not constant or same for different wavelengths. It is different for different x-rays. Okay, and if you have fixed the x-rays and you are changing the scattering angles, or it means the incident angles, you are changing the angles at which you are bombarding x-rays on the crystal, then the atomic scattering factor will be affected by this thing as well. Hence there is a dependence of atomic scattering factor on these things as well. And if we have kept these constants, if theta is constant and lambda is constant, we have fixed that, then we will get a fixed atomic scattering factor for an element. But if we keep changing it, then the scattering ability of atoms will change depending upon the values of theta, ratio, lambda, and sign of it. Roughly, approximately, we can say that f decreases with increase in theta, but precisely what the relationship is, that f decreases as the increase in value of sine theta by lambda. Okay, so we can write it like that. There is an inverse relation between these two quantities. This f is inversely proportional to sine theta by lambda. But if the atom was a point-like object, if the electronic cloud wasn't a thing and every electron is stacked over each other, then there will be no more dependence of atomic scattering factor on the scattering angle. Okay, so there will be no more dependence. For example, if you consider a neutron scattering from atomic nuclei, since atomic nuclei is uh, more approximately, we can say it is acting like a point like object, since it's really dense and really small in size. We can all can take it as a point object. Atomic nucleus can be taken as a point object. So neutron scattering from atomic nucleus works like that. It doesn't depend upon the scattering angle. Its atomic scattering factor doesn't depend upon the scattering angle, because of the reason that the atomic nucleus is more like a point object. There is no preference to position or angles. Okay, so if here in that case as well, if the electronic cloud was a point like thing, then they would never have been a preferring angle. I hope you are understanding what I mean to saying preference. Okay, preference means that there is a relation of scattering factor with the scattering angle. So you can write this statement here as well. If the atoms were point like object, point like objects, then there would not be dependence of scattering factor, atomic scattering factor, on scattering angle. For example, we can give example of neutron scattering, which is a real case. Neutrons are scattered by atomic nuclei. Neutrons are not scattered by electrons. The reason is neutrons are neutral and they do not interact electromagnetically with electrons. They only interact with atomic nucleus because there are other neutrons in there, and they do interaction through strong force. Neutrons are scattered by atomic nuclei rather than by electrons around the nucleus. Since the nucleus is very small as compared to the size of the atom, it can be treated as the nucleus can be treated as a point object. The scattering for a non-vibrating nucleus is almost independent of scattering angle. We said almost because we are saying nucleus as point object approximately, which is not a fact but an approximation. That is why we said approximately or almost it is independent of scattering angle. There is a small influence of scattering angle on the scattering factor. Here we wind up our video. This is all we can write about atomic scattering factor so far, and its derivation is pending. If you want me to upload a video on it, then please comment. I'll do that, and let me make you people understand this definition that I told you people that I will do it at the end. So this is the only part that I need to justify, I hope, because I was justifying the other statements side by side. Though the atomic scattering factor is the measure of the efficiency of an atom in scattering the X-rays. Mathematically, it is the ratio of scattering amplitude of X-rays scattered from a single atom or electronic cloud to the scattering amplitude of the X-rays scattered from a electron located at a point. It is the comparison that we make, that how well an electronic cloud, the whole cloud, can scatter as compared to a single electron. Okay, we compare the ability of many electrons system to a single electron, and this many electron system has position dependence as well. The electrons that is present at this location, the electron that is present at this location will have different ability to scatter the X-rays than the electron present at this location. Okay, so all of the electrons are distributed at different positions, and we have this radius r, and they're all different. Okay, r1, r2, r3, r4. So each electron's ability to scatter the x-rays is different, and we sum it up. Okay, we sum it up to find out the ability of the whole cloud. This is something that we write in numerator, divided by the ability to scatter the x-rays by a single electron which is at same position, at particular position. So we see that how well the electronic cloud is scattering as compared to a single electron separately. Okay, this is just a comparison that how a team would work. Teamwork compares to a individual work. This is the simple definition that we can give. Since the electronic cloud is also an atom, so we also write it as atom. So we can calculate it by different ways. Total effect by the whole team as compared to the individual team, or the scattering amplitude of the x-rays from this whole cloud as compared to this single electron. And we can calculate it easily by using the integral formula, and different ways are there. So yeah, I hope you got the definition. It's just a comparison of how well a team would work as compared to a single member in terms of electronic density. And yeah, this is all clear. And yeah, thank you so much for watching my video, and if you like it, please give me a thumbs up, comment, share, and subscribe. Thank you so much.